Alright, welcome to the first video for Chapter 9. We're going to start with Section 9.1, obviously. This is our first introduction to inferential statistics, where we're really going to do the analysis of what statistics is all about. This is what we've been working up toward. So we can actually do some analysis, do some inferences about what statistics means. Let me see if I can turn on a light here. It seems kind of dark. See if that's any better. Give me a little front lighting there. So the two main topics here, we're going to construct what's called a confidence interval, and we'll explain what that means. And then toward the end, we're going to determine a sample size necessary if we want a specific margin of error within that confidence interval. So these things we'll explain more as we get in. This is all going to be based on the distribution of the sample proportions. We did that back in Chapter 8. We know that if I do a sample proportion, collect a sample, I'm not always going to get what the true population proportion is, but I can expect to have a mean that is that same true population proportion, and I have a standard deviation, the square root of p times 1 minus p all over n. And then there were certain conditions that needed to be met. So let's look at a particular example. We know that according to ECC's data, 69.3% of ECC students are part-time. So let's say we take a random sample of 100 students. The question is, what will be the distribution of the proportion of that sample who are part-time? Now, we can't get 69.3%. We have 100 students, so it's either 69% or 70%, maybe 67% or 72%. How are those proportions going to be distributed? Well, using the formulas, we know that the mean should be the mean of the population, or the proportion of the population. So if we average all of our sample proportions, we should get 0.693, and the standard deviation is about 0.046. So if those conditions are met, which we have here, 100 students is less than 5% of the population, and n times p times 1 minus p is at least 10. So we should have a roughly normal distribution for that sample proportion. We would expect a mean of 0.693 in the middle. And then if we think of the empirical rule, we'd expect 2 standard deviations each way. So if we add 2 of those, what was it, 0.046, which would be 0.092, if we add that on to the right side and to the left side, we would expect then about 95% of the sample proportions to be within there. Sometimes they'd be low end, most of them would be in the middle, but some might be at the high end. So 95% of our sample proportions, about 95%, should be within 2 standard deviations. So the idea of a confidence interval is you start with what your estimate is. In this case, if we don't know the population proportion, which is usually the case. Here I gave you the college's data of 69.3%, but usually we're taking a sample, we don't know that. So our best estimate is our sample. And then minus kind of margin of error. In this case, if we went up and down 2 standard deviations, we would call that our margin of error. And so we have a 95% confidence interval is approximately our sample proportion, p hat, plus or minus the margin of error. So let's say we did this and we took 20 of these samples and we did this plus or minus 2 standard deviations each time. I've just got a visual here. We would expect most of the sample proportions to be in the middle, right? We'd expect 0.693, sometimes a little bit low, sometimes above, but we'd expect most of them to be in the middle. In fact, we'd expect if you did 20 of them, you'd expect 95% of the sample proportions to be in the middle. So if I use that 2 standard deviations each way, if I'm in that middle, if I'm within 2 standard deviations, my confidence interval includes the true population proportion. Sometimes, though, it doesn't. So I have this example right here that does not include that proportion, but the rest of them do. 95% of them do, because 95% of the sample proportions are in here. So if I use a width of 2 standard deviations, 95% of the time I'll catch that true population proportion. Now, The downside is you're only going to do one sample, and you're not going to know what the true population proportion is, so you're not going to know if you caught that or not. What you're saying is, okay, I'm 95% confident that I'm going to contain the population proportion. You know, if I did this over and over and over, 95% of confidence intervals like this would contain the true population proportion. In fact, let's go to the next slide. That's what it means here. It's difficult to kind of separate this from probability. If I look at my interval, I find my point estimate, I do plus or minus, that's my confidence interval, and I say, well, I'm 95% confident that the proportion is in there. It's not a probability. Either the proportion is in here or it isn't. It's a 0 or a 1, and we don't know. But if we repeat this process over and over and over, 95% of the confidence intervals like this will contain the true population proportion. Okay, so what about other confidence levels? We do 95% a lot. That's kind of the typical one. But what about 98% or 99%? A 95% confidence interval was within 2 standard deviations. So let's see if we can get more precise about where that 2 standard deviations came from. We talked about it coming from the empirical rule, but we know more than the empirical rule now. We've been talking about the normal distribution. And so let's dive in a little bit deeper here and think about that too. So I used StatCrunch here, and I just did the normal distribution with a mean of 0 and a standard deviation of 1. So that's a z-score. And I put an area of 0.025 to the right. So 95% in the middle, 2.5% on each tail. And so it's actually 1.96 standard deviations. Very close to 2, but not exact. So 95% of all the sample proportions are in the middle, and then 2.5% in each tail. And so if you have 1.96 standard deviations, if we're really precise, then that upper limit would be the sample proportion, whatever our estimate is, plus 1.96, and the lower would be minus 1.96. In fact, hold on here. That should actually be, oops, P and P. So 95% of all sample proportions are within the true population proportion minus 1.96, and then the true population proportion plus 1.96 standard deviations. What about the more general case? So what if we put 1 minus alpha in the middle? This is the alpha, seems kind of weird notation here, but alpha is a small number. It's like the remainder. It's really alpha over 2 in each tail. In that case, that width to get, it's not 2 standard deviations now, it's a z-score, and it's a z of whatever that area in the tail is, so it's z alpha over 2. And again, I got to change my slides here. Sorry about that. Jump back in. There we go. And so if we have our true population proportion and we add, instead of 2 standard deviations, we add this number of standard deviations, that'll leave 1 minus alpha in the middle. So alpha over 2 in this tail, alpha over 2 in this tail, so 1 minus alpha, everything else is in the middle. So if we have like 95%, alpha is 0.05. So there's 2.5% in each tail, and that's how we got the 1.96 standard deviations. Incidentally, if you're feeling a little overwhelmed, we're going to use StatCrunch to calculate these. So don't stress about it too much, but it's important to understand what StatCrunch is doing here, that it's number of standard deviations. Okay, there's one problem. All of these assume it's this number of standard deviations, and you can calculate the standard deviation. But the standard deviation formula includes P, which we don't know. The whole point is we're trying to find a confidence interval for P. So we're going to include a little bit of fuzziness in here, and we're going to use the next best thing, which is the sample proportion. And so we're going to say that this standard deviation is approximately equal to, if we replace that P, which is our unknown, that's the whole point, with the sample proportion. And so then we create this confidence interval that's our point estimate plus or minus the number of standard deviations. So z alpha over 2 is the number of standard deviations, and then we multiply by our estimate for the standard deviation. And again, we have these conditions that need to be true. A sample size has to be less than or equal to 5% of the population. And n times, in this case, p hat times 1 minus p hat has to be at least 10. All right, so let's talk about StatCrunch, and let's do a few examples. So in StatCrunch, we're going to go under Stat and Proportion Stats and do one sample with summary. And I'll do some examples of this in a bit. And then we just enter in how many successes, how many total observations, and then click the confidence interval. So let's do an example. This was from a Pew Research poll, a little outdated now, 2014 July, but talking about people's view of the economy. And we have three different proportions we're going to look at. 19% rated the conditions as excellent or good, 46% they were only fair, and 35% said they were poor. The question is, okay, it's going to report a margin of error. Technically, if we do a confidence interval for what percentage of Americans believe this, each one of those would have a confidence interval. Okay, we think it's 19%, but plus or minus this. We think it's 46%, plus or minus this. But they're not going to report three of those. But let's do all three and then see which one. Let's see if a trend pops up for what we might report as kind of an average margin of error. All right, so let's go over to StatCrunch. Oh, I passed it. Here. And so we're going to go to Stat, Proportion Stats, one sample with summary. Now the problem is we need number of successes. So we are going to have to calculate what is 19% of 1,805. So it must have been 343. So 343 out of 1805. And we're going to do a confidence interval and hit compute. So we have about 17.2 to 20.8. And I'm going to just repeat this. Let's see, the other one was 46%. So that must be 830. And that would be 43.7 to 48.3. And I have these in the PowerPoint. So hopefully you printed that out. You should be able to see them there. 35% gives us 632. And that gives us 32.8 to 37.2. So for the 19% margin of error, the confidence interval was 17.2 to 20.8. So that's the full width. You can either take half of that to get the margin of error, or you can say, well, if the center point is 19% and it went up to 20.8%, the margin of error must be the difference, 1.8%. Same thing for the other one, 46% and 35%. So you can see the bulk of these margins of error, it's about 2. So based on those, it should probably report a margin of error of 2%. They kind of lump those together and say, well, the margin of error on this is 2%. All right, next one. Another outdated one here. I did some of this research a couple summers ago. I did my first draft of these. This was before the last gubernatorial election. So up for election here, and oh, that's like a weird shadow there. Maybe I don't want that light on there. I'm just realizing. I'm going to turn this light off and see. Whoa, that's a weird shadow. Come on, turn off. And now I'm dark, but it is a weird shadow. Sorry, this is the second version of this video. I'm not making another one, so hopefully it's visible. All right, so this writer said that the race for governor was a dead heat. So like a statistical tie. What does that mean? Because if you look at the poll, Rauner has a clear lead. So why would they say that he's in a dead heat? Well, if you do the same thing here and you say, well, 45% of 800 and do the margin of error in StatCrunch and 43%, and you find these confidence intervals, what's interesting is that Rauner has a 45%, and it goes from 41.6% to 48.4%. It's a 3.4% margin of error. This one is a much larger margin of error because they only polled 800 people. So less people, larger margin of error, more uncertainty. Quinn had a proportion of 43%, and with that margin of error was also 3.4% for his because they were very close. And what you'll see, obviously, what I'm trying to illustrate with this visual is that there's an overlap. So we can't be certain who has the lead. Now the likelihood is that Rauner has the lead because his sample proportion was higher, but boy, Quinn could have had as much as 46.4%, Rauner as low as 41.6%. Quinn could be a huge lead. So when you have this margin of error of 3.4% and the difference in the two is only 2%, certainly we don't know really who is in the lead because those margin of errors, they overlap there. And so that's what they mean by dead heat here, that they're really in a statistical tie. Okay, last thing here, a couple more slides. Sometimes we want to work backward. So sometimes we say, you know what, I want a poll that has a margin of error of 2%. How many people should I survey? So if we look at that confidence interval formula, and just that last part is the margin of error, so we're going to call that E, the margin of error. If we do a little algebra, square both sides, divide, do a reciprocal, and solve for n, we get this formula here, that n is p hat times 1 minus p hat, and then this formula here. So we can find the sample size that we would need under certain conditions. The problem is, what do we use for p hat? So if we want a certain margin of error, and we want a 95% confidence interval, we can calculate all this. So there are two possibilities. One is you have a similar poll you've done in the past, and so you can use that as a guide for what p hat will be. The other is just say, you know what, I know nothing, I'm going to go worst case scenario and use p hat as 0.5. There's actually some interesting algebra here that you can show that a p hat of 0.5 is the worst case scenario. It gives you the largest sample size that would take care of this for you. All right, so let's do an example here. We've got this information about the Office of Institutional Research at ECC. We do lots of surveys of students, and one that we do, I think, every year is student satisfaction. So suppose we want to get a 95% confidence interval for the overall satisfaction. We want to be really certain. We want that margin of error of our poll to be at most 2%. So we want to say, you know what, whatever overall with ECC, but we want to be really certain, so 92 plus or minus 2%. The question is, how many students do we need? And we're going to do it with two conditions. One, that we use the previous year's survey result that 82% of students were satisfied. And what if we don't use any previous results? All right, so let's get in here. The 95% means our alpha is 0.05. If we want the confidence interval, the error, to be 2%, that's the error then will be 0.02. And one option here would be to use a previous year sample proportion for 0.82 for the p hat. And if we don't use any previous results, we'd say p hat is 0.5. So we're going to use that formula, and so I've got the two different versions here. One would be if we use the previous year's results. So we have p hat times 1 minus p hat times z alpha over 2 all over e squared. And this z alpha over 2, you recall, we've got alpha is 5%. So that's the area in the tails. Let me go over to StatCrunch. That's the area in the tails. And so what we want then is half of that on the right. So we would do half of that, 0.025, and that gives us this z. Actually, that was the one on the left. Of course, to the right, it's just the opposite of it. So there's 1.96. So that's that z. And if we don't use any previous results, we would just use p hat as 0.5. And you can notice here we get a lot larger sample size necessary. So if we're not sure where our students are going to fall, we have to sample a lot more. If we're pretty sure that it's going to be around 82%, you know what? About 1,420 students should do it for us. If it's very different from 82%, then we might not get that small margin of error that we want, because we're not going to actually know the margin of error until we do the calculation. But we can kind of get an estimate for how many students we need in preparation for that. So, long video, big section. The rest of Chapter 9 will be next week, and that'll be a little bit easier. There's more of it. There's more sections, different confidence intervals. But once we get the idea of a confidence interval, they will hopefully be shorter. So I apologize for the length of this particular video. But that's it for now. Hopefully you get a chance to look at this before class, and we'll talk about questions in class.